All right, good evening, everyone. Sorry to be so late this evening. I was trying to get some things done. So from the last class, we have been looking at factorization of quadratic. Today, we're going to be still doing factorization, and pretty much we're still on quadratic. But we're going to be looking at a special type of quadratic that we generally identify as what we call perfect squares. And so in factorizing perfect squares, we still can use the AC method. However, we can actually use a different technique once we identify that the expression is a perfect square. And so this technique can save us a lot of time rather than going through the AC method. So we're pretty much going to first start off by looking at why we call this quadratic expression a perfect square, and actually what the technique is that we can use instead of the AC method. All right. All right. So first, let us get into the whole idea of perfect squares. All right. Now, oftentimes the geometry, oftentimes the algebra that we're dealing with, quadratic expressions, they often can be related to a geometry, or can be related to geometry in the sense that we can relate them to either a rectangular shape or a square shape. Now, why is this so? And I'm going to point out that using this illustration. So we know that a perfect square in geometry has to do with four-sided figure, which has all the sides equal, and we have four right angles, right? That's pretty much what we define as a square. And so what we're seeing here would be what we would refer to as a perfect square. Now, from an algebraic point of view, we could actually find the area of this square if we are using the variable x as the length of the side of the square. Because the area of a square, anybody know what the area of a square is? Ms. Clark, do you know what the area of a square, what the formula for the area of a square?
Sir, to be honest, I don't remember.
Okay. Miss, let me ask, Miss School Spring, do you have any idea what the formula for the area of square?
No, sir, I don't remember.
Okay.
Sir, it's width times length.
Okay. All right, so the formula, as Miss Williams is saying, was that you, Miss Williams?
Yes, sir.
Right. The formula is pretty much the same as the formula for the area of a rectangle, which we generally say length times width. Now, it's a little bit awkward to kind of use length times width for square, because what we know is that the length and the width would have the same pretty much length, right? So the width and the length have the same length or the same measurement. So instead of saying length times width, when we're referring to area of a square, we would just say length times length, right? And so in this case, if the length is x, and we know that all the sides of the square would have length x, and if the area is length times length, then pretty much the area of this square with length x would be x times x, which is x squared. And everybody will agree with that. Let me see the hands if you're agreeing with what is being said here. All right, very good. Now, length times length based on this square would be based on each side having the length x. However, if we construct a square as the following, where it is still a square, however, the length of this square would be the sum of two lengths. So if we look at what this diagram is portraying, now when I know it doesn't look perfectly like a square, and so in mathematics, when we draw something that is not dimensionally correct in terms of the measurement, we generally say that it is not drawn to scale. So if it is not drawn to scale, that means the measurements are not absolutely accurate. All right, so for this square, not so much looking exactly like a square because it looks a little longer lengthwise than widthwise, but anyways, we are assuming that all the sides here are the same. However, if we take out a portion of the length, and then now label that portion of the length A. Let me do this a little more accurately with a line. So if you call the length from here to here, we call that length A. All right. Now, remember in algebra, when we use a letter or a symbol to denote or to represent a number, we oftentimes don't know what that number is. And so it is a general value. So let's say that that length represents a number A. Then also, if we should look at the other portion, we could also draw a length from this portion to here and call that a length B. Now, that length B plus the length A would give you the full length of the square. And so we can actually say, all right, the length here would be the sum of A plus B. Because this length A plus this length B would just give you A plus B. Because in algebra, when we don't know exactly what the terms are, and if they are not like terms, we generally leave them as an expression with a plus sign between them. So if it is a square and one side is A plus B, it's a binomial expression, and the other side, being a square, would also be A plus B. Now, if we are to, say, find the area of this square, then we would have to multiply length times length. And if we multiply length times length, then clearly we we can see that A plus B all square would actually give you A plus B times A plus B. And so that would be the area. Now, however, this is a binomial term. And what happened is if we're squaring any form of number, we're actually multiplying the number by itself. And in this case, if we're squaring this binomial, we have to be multiplying the binomial by itself. So if we multiply the binomial by itself, then we would multiply A plus B times A plus B. And if we follow the law that we would have learned about the distributive law when we're expanding binomial, then we would multiply A times A to give you what? A squared. And we kind of revert to the color that I've always been using. So A times A would give you A squared and then we have A times B, and then remember now we're keeping the sign, so that would be plus A times B give you AB. All right, then now we use B times A, but B times A is also the same as AB because the order doesn't matter. When we're multiplying two numbers, the product will always be the same. So A times B and B times A are exactly the same. So we can just call both of them AB. Now B times B would give you B squared. So it happens that when we multiply the two binomials, this is how our expression look. Now, if we simplify the expression by adding the like terms that we have in the middle here, then what we will end up having is A squared, and I hope you all can see down here. If you cannot see, please let me know. All right, so we'll have A squared plus 2AB plus B squared. Everybody see that? Let me see a hand if you're all following and you see how we arrive at this answer. All right, so only two persons see what is happening, guys. We're still going back to the binomial expansion that we would have done from previous class. And so we are multiplying our two brackets. And so we do just as what we would have learned when we are multiplying with binomials. It's the same process that we are following. All right. So once we have done that multiplication, then it would have expanded into the product of A squared plus 2AB plus B squared. It turns out that whenever we square in a binomial, the expanded form, which is the product, have this similar feature. Now, the feature that is similar for all binomial that is square, the feature would be that you would get the first term in the expression, the first term in the binomial would be a square term in the product. And the second term in the binomial would be the last term square in the product, because this is the product after we multiply out the two binomials. Now the middle term is 2 times the first term times the second term. So that's a general feature of when we are multiplying the squares, when we are multiplying a binomial by itself. And it means that once you square the binomial, it will give you this general feature. And because we are using the geometric idea of a square, and if you're multiplying the length times the length, then you will get a square. And so we refer to this quadratic expression as a perfect square. So the perfect square expression has 2 forms to it. It has the form in the factorized form. So this is the binomial in the factorized form. Now the factorized form also can look like this, because the factorized form would be the product of 2 factors. And the factors here would be a plus b times a plus b. But oftentimes, we can easily identify when it is in this form, because we notice that we have a plus b all square in brackets. So this is, we would refer to this as the factorized form, which also can look like this, all right? Now, the expanded form mean after we multiply it out, we would get it to look like this. So for perfect square, the factorized form look like this, and this part here I would have down here would be the expanded form. Now it is important that you're able to identify both the factorized form and the expanded form of a perfect square, because it is these features that we are going to rely on to know whether or not we can apply that special technique how to factorize it. As remember, I said that this can be factorized by the AC method. However, we're going to use a special method based on the features in the expression. And so that's what we're going to be looking at now. All right, so we're going to just take these features and relate them to factorization, right? So in general, perfect squares are of the form, and this is the general form. And remember, I said to you that this would have been the factorized form, and it can be, the factorized form can also be written in this form. But to simplify it, we generally say that you're multiplying the expression by itself. So we simply just write it in this form, right? So oftentimes when you're looking for a perfect square, you want to see that you have a first term and a last term in brackets, all square, with either a plus or minus sign in between them. When you expand it, it's going to look like this. The first term going to be a square term, first term from the brackets, going to be square in the expanded form. The second term from the binomial in the brackets going to be a square term. The last term square in the expanded form. But the middle term, you're going to realize that the product of the 2 terms times 2 will give you the middle term. And so these are the features that we are going to take to identify our perfect square. Now, when we have these features of a perfect square, it is very much easy to get from the expanded form back to the factorized form. Very easy to get from this back to that. Because all we need to do to get from this form to this, from this expanded form back to the original form, all we need to do is to bring these bases. And notice I'm saying you bring down the bases. Now, when we say the bases, we are referring to the base without the power. So you bring down the bases in the brackets. So you bring down A here without the power. You bring down B here without the power. And then you bring down the sign of the middle term. Bring down the plus sign here. And then now the squares are the square that you would have, you would put outside the brackets. And you see that from the expanded form, we can easily factorize it back to this by just simply bringing down the bases in bracket, keeping the sign of the middle term, and bring back the power outside the bracket. Raise your hand if you all see and understand what I'm saying about how to easily factorize a perfect square. Let me see your hands. All right, so just to get a little bit of clarification from you, I'm just going to call on Ms. Waysom. Can you just explain to me what I just explained to the class?
Yes, sir. All right, so you said in the case where we have the expanded form, which is a squared plus 2ab plus b squared, to get it back to the general form, we would just bring down the variables, the base. That would be a, keep the sign of keep the middle sign, which would be plus the positive sign, and then bring down.
Let me just illustrate as you're saying it. So
yes,
we open brackets.
Yes, sir.
Then we bring down the base without
the base, which would be a by itself.
Without the square.
Yes, sir.
And the A, you put
keep the sign of the middle one.
And you keep the sign of the middle term. And what?
Yes, sir. And then you put the power outside, which would be the square.
All right, then you put the power outside, and that's how easy it is to factorize a perfect square. It's very easy to factorize a perfect square. Now, remember I was saying too, that you could also apply the AC method. So alternative to using this method, we could have used the AC method, but of course, from previous experience, we would have noticed that the AC method would take a little longer time, right? Because we'd have to multiply A times B, find two factors of A times B, which when you add it to get the middle term, and then now you have to replace the middle term with those two terms, then you factorize by grouping till you get down to this, which would be a longer process. Do you agree with me? Let me see your hands if you agree that that would be a longer process. Right, because that's what we were doing the last class. You were actually carrying out the AC method. And we know that it would take a little while to complete that factorization process. So because we know that this is a technique that we can use with perfect square, and this technique can only be used with perfect square. It cannot be used with the other quadratics that are not perfect square. So it means that because it only can be used with perfect square, we have to be keen on the expression. We have to be able to look at it very carefully and identify the expression first as a perfect square before we apply this technique. And so knowing these features about perfect square pretty much is what we have to look for before we carry out this process the shortcut method of factorizing. All right, now, so the perfect square can appear in this way, or it can appear with a minus sign between the two terms. So when you have a minus sign in the factor form, I'm calling this the factor form, and we're calling this the expanded form. So when there's a minus sign between the binomials in the factor form, then you notice that in the expanded form, the middle term also has a minus. Let me see the hands if everybody see what I'm saying. You notice that? Right. Now, so the key features then of the perfect square is that from the factor form, if there's a plus in the middle, then the expanded form, the middle term, must also be a plus. From the factor form, if there's a minus sign between the binomials, or in the middle of the binomial, then the expanded form middle term going to also be a negative. All right. Now, the other feature that we notice is that the middle term would have a coefficient of 2 times the product of the two terms. So there's always a multiple of 2 in the middle term of a perfect square. Now, even though we are able to see this 2 very clearly in these two forms, it won't be so obvious for all perfect square where the middle term you would see a 2, all right? Because based on what the middle term is, sometimes it can multiply with some other number where you don't actually see a 2, and that's where it becomes tricky. And so in that case, you have to be able now to from that, determine whether or not you really have a perfect square. And so that's the first part that we want to be able to do. We want to be able to look at an expression and first determine that the expression is a perfect square. And once you have identified it in that sense, we can go ahead and use the shortcut technique that we just looked at. All right, so a perfect square of an expanded binomial expression consists of the following properties. So the first term is a square term. And as we know that the first term square would be what? The first term in the binomial would become the first term square in the expanded form. And we look at the middle term, we see that it is 2 times the first term times the last term. So what we're saying is that the first and the second term in the binomial, if you multiply those 2 terms and then times it by 2, you get the middle term. And then we also notice that is the last term in the binomial. In this case, the b would be the last term in the binomial, would become the last term of the expanded form, and it would be squared. And so these are the features that will guide us to know when we have a perfect square. All right, so let us now look at the steps. So to factorize perfect square, step 1 says that we first check by inspection, meaning that you have to look for the features that you would have learned about a perfect square within the expression. So you check by inspection to see whether or not the expression satisfies the properties of a perfect square. And in that we mean that we are checking to see if the first term is a square term. We are checking to see if the last term is a square term, and we are checking to see if the middle term is 2 times the first term times the last term. And so if you're looking at this expression and see the first term, which is a square term, the last term, which is a square term, the middle term going to have 2 times the base of the first times the base of the last. When I use the term base, I am referring to the term without the powers. All right. So then the expression is a perfect square once it satisfies this general form. All right, now it is easy to factorize a perfect square because you just simply what? Rewrite first term and last term as square term. And step 3, then we factorize by bringing down the bases of the squares in brackets. And we square everything in the bracket. And so that is what we were looking at just now when I was illustrating how to factorize it. So perfect square can also be factorized by the AC method. But we are not going to be focusing so much on the AC method today. Now, when we look at this expression here, can we safely say to ourselves that this expression is a perfect square? Let me hear a feedback or a response from somebody. Can we say that this expression is a perfect square? And why? Miss Cox, is this expression a perfect square?
Sir, yes.
All right, so you would have to clearly give me some reason why you say yes. What is the reason?
Sir, because all of them are one square.
When you say all of them, like what you're referring to as all of them?
Sir, 9a squared. Oh no. Sorry, sir. Sir, I don't know why.
Oh.
Maybe sir, I don't know.
All right. So when you're looking at this, you're trying to compare it with the two general form that we would have looked at previously. All right. But the only difference with these now, you notice that you may have coefficients for the first term and the last term. All right. Let me find out from anybody else if they recognize this as a perfect square and why. Ms. Wasom, do us the honors. Is it a perfect square?
Yes, sir.
All right, give me the reason for your answer.
For the first term, sir, it is squared, and the last term is squared as well.
All right.
And it says that a perfect square in an expanded form can be identified by the first term being squared and the last term being squared.
All right, so how you come to the conclusion that the first term is a square term?
Because you have a 9a square, sir, and then middle look on it said 9 can be squared as well. 3 is 9.
And what else?
And the same thing for the last term. The 4 can be 2 times 2, which is 4.
All right. Let me see the hands of anybody else who have made that observation. Anybody else would have seen what Ms. Wasom just described? Only Miss. All right, Miss Cox. Do you see what?
Yes, sir.
Do you see what Miss Wasom is saying?
Yes, sir.
All right, Miss Clark. Are you seeing what Miss Wasom is saying?
Yes, sir.
Okay. Miss Lang, seeing what Miss Wasom is saying? All right, so it is not quite obvious that this is so, but one of the things that you have to consider when you're looking at when you're trying to determine if an expression is a perfect square, then first you look at whatever coefficient, which the coefficient is just the number in front the variable. So you look at the number in front, the first term and the last term. And obviously you want to look at the variable itself, which is the A and the B, and you want to look at those and see if those are square terms. So the A has a square, the B has a square. Obviously, the A and the B, they are squares. Now, what about the numbers? Can the 9 and the 4 be written in a square form? What would you write as what number would you square to get 9?
3 square.